What role does feedback play in stabilizing unstable systems? Imagine a system that starts to wobble out of control, like a spinning top that's about to fall over. Without intervention, it could spin faster and become even more unstable. Now, think about how engineers keep such systems steady. The secret lies in feedback. Feedback is when a system takes part of its output, checks it, and then uses that information to adjust what it's doing. This process is like a driver constantly looking in the rearview mirror to keep the car centered in the lane. In electrical engineering, feedback is essential for systems that tend to behave unpredictably. When a system is unstable, small changes or disturbances can cause huge deviations. Feedback helps by monitoring the output through sensors and comparing it to a desired target or set point. The controller then processes this difference, called the error, and makes adjustments to the input to bring the output back in line. This creates a loop where the system is always checking itself and correcting course. There are two main types of feedback. Negative feedback subtracts part of the output from the input, which reduces errors and helps the system settle down. This is the most common type used in control systems because it works to stabilize the system. Positive feedback, on the other hand, adds to the input and can make deviations worse, leading to oscillations or even system failure. That's why positive feedback is usually avoided when stability is the goal, unless you want the system to oscillate intentionally, like in oscillators. In control systems, sensors measure things like voltage, current, or speed. The controller then uses algorithms, often called proportional integral derivative control, to decide how to adjust the system. Actuators then carry out these adjustments, like changing the voltage or motor speed. This cycle repeats constantly, allowing the system to reject disturbances, adapt to changes, and stay stable even when external conditions vary. From a stability analysis point of view, feedback changes the system's characteristic equations, which determine how the system behaves over time. Properly designed negative feedback shifts the system's poles, points that influence stability, to locations in the complex plane that ensure the system doesn't grow unbounded. Engineers use tools like root locus plots, Nyquist diagrams, and frequency response methods to visualize and verify these changes. In real-world electrical engineering, feedback is used in voltage regulators to keep output voltage steady despite load changes. It's also used in motor controllers to maintain constant speed under different loads, and in amplifier circuits to stabilize gain and reduce distortion. Feedback acts like a safety net, constantly correcting and maintaining the system's stability. So, in simple terms, feedback plays a vital role in stabilizing systems that would otherwise become unpredictable. It keeps the output in check by continuously sensing, comparing, and adjusting, ensuring systems run smoothly and reliably. This process is at the heart of control systems, making sure everything from power supplies to motors works as intended, no matter what external changes come along.